All right, so one last thing. Let me make sure my volume is where you can hear me. Okay, good. All right, so one last thing before we start on this next assignment. All the trig review kind of comes back to this. How do we use trigonometry in physics? We use it in terms of vectors and breaking things up into component vectors. Okay, so vectors are really key here. And eventually, when we have our triangle, like so, right? If we have a resultant vector in here, and actually what's usually going to look like, let me put that in a here's our x, here's our y, and we'll get some kind of a value like that for a vector, okay? And then I'm going to ask you guys to split it up. I'm going to ask you to find the x piece and the y piece so you can start adding those together. And again, the way you do that is using trigonometry. If you know the angle, your theta right there, you can figure out your x and your y piece, your x, and then your y component vectors to that resultant, or that position vector, okay? So how do we add up multiple vectors? What if we have a situation like this? Okay, so let me draw this out a little bigger. So we actually have two vectors. We have a vector like that, call it 1, okay? And we actually have a second vector. Maybe this is two forces pushing on something. Maybe this is two velocities. Maybe this is two accelerations on a single object. How do we add these things up if we have things like this? Well, that looks difficult at first, doesn't it? And I bet you're probably scratching your head as to how the heck you manage that. Well, it's actually not that bad, okay? So remember what I already told you, and I already told you some of this when we were talking just about triangles, okay? If I want to take and add vectors up, if I have, let's say, two component vectors, I have a y vector and I have an x vector. Remember this? If you take and move the x vector up, so it's up here, you will get your resultant vector like so, okay? And it doesn't matter if you move the x or if you move the y. If you move the y instead of the x, you'll get the exact same thing, right? You will have the same resultant vector, okay? So it turns out this is no different. This is absolutely no different. We added two vectors here to get our result. Now we have two vectors, so what are we going to do? We're going to add them up. Graphically, the easiest way of doing that, I'm going to move these over here, right? So I have one that's going something like this, right? And I have two that is going something like, this, right? So how do I add those together? First way is graphically. If you're very careful, you get a ruler out, you get a protractor out, measure the correct angles that those are making, to your coordinate systems. You get your angles in there, make sure that everything's good to go, and you can actually do this and get an accurate answer. So just like we did here, you're going to need to move one of those vectors over, okay? So let's say I go ahead and move 2. So what do? I move 2, but I move it so that the tail of it is touching the head of 1, okay? So the tail of 2 is here, and if I draw it exactly as it is here, and it's totally going to be exact, right? I'm not going to screw this up at all. So that's 2 scooted up so that it's at the head of 1, okay? So what does my resultant vector look like? Well, it looks about probably like you'd expect. You go from the tail of 1 to the head of 2, and you get a resultant vector like that, okay? What if you did it the other way? Okay, I left 2 in place, but I'm going to move 1 around. Does that matter, Mr. Casey? Well, no, it doesn't at all. It's the same thing as what we did here. If I take and scoot 1 along so the tail is right at the head of 2, and I draw that in, I will get the exact same answer. I end up with these things ending at a point here. And your resultant vector really goes from 0 to the point at which you finish. So you end up with the same resultant vector either way. It's okay. So graphically, you get the exact same thing. So that's vector addition. Okay, graphically. What about subtraction graphically? Okay, this was 1 plus, I'll draw this in color so you can see it, 1 plus 2, and that gave us our resultant vector, which I'm calling r, right? What if we did this? Instead of 1 plus 2, what if I did 1 minus 2? So I was going to do that in the correct colors here, right? What do I get? Well, let's see, okay? So first things first, what you need to realize here is that I've actually done one thing different. I've introduced a minus sign, okay? So what I actually have is I still have my vector number 1, but now I have a second vector, and it's actually, that second vector is a minus 2, okay? So when I'm putting these together, it's still vector addition. I'm adding a 1 plus a minus 2. How do you do that? Well, I'm glad you asked. So I'm going to draw my x and y. Okay, we had our vector number 1 was up like this. Okay, there's vector 1. And we had vector 2, which was something like this. How in the heck do we add those things together? Well, we have to take first and make 2 what it is in our equation. We have to make it a minus 2. So we always start at 0, okay, or we probably will. Whatever your starting place is, keep it the same, okay? But we have to take and we have to make this a minus 2. That means it has to get flipped around, okay? So we're going to take and make a mirror image of it. We're going to draw the same length, but going in the opposite direction. So there is our minus 2 vector. See what I did there? All I took was this and flipped it around on its head, okay? So if that's what I have, is I actually have a 1 plus a minus 2. Okay, so now I do the exact same thing I did before. So I have my vector 1, which was up like this, and I had 2, which was off like this. So how do I add them? Same thing I did before. I just take and drag one up to the top of the other. Right? That's kind of poorly done. So I move that up. My resultant is from the start of this guy, from the start of our origin of these, right, up to my final point, and that's my resultant vector. Okay? And you can see now that this R looks very different from that one. This one got longer, okay? This one kind of got shorter and changed direction. All right? So, what if I took and slid this over? Well, again, I could take and instead of having moved minus 2 around, I could move 1 over. I could move 1 over to the head of 2. And if I do so, I'll still end up with a line that ends in the same place. This is still vector 1 and minus 2. Add them together that way. Make it a dash line so you can see I moved it. And you still get the same resultant vector. Now, interesting question. Is one vector, right, vector 1 minus vector 2, the same as 2 minus 1? When we added them up, it made no difference, right? What about when we take and we move it around? So now, I'm going to do this. I'm going to do 2, and let me keep my colors, vector 2 plus a negative 1 vector. And realize that I could write this as 2 minus 1, right? It will still get me the exact same thing, right? What I've done is I've flipped 1 around, okay? So let me draw my origin again. So here's my xy. I had originally vector 1 up like this, and I had vector 2 off like this. This is 2, this is 1. So if I want to do this subtraction of 2 minus 1, or a negative 1 plus 2, what I will get is I have to get, in either case, a negative 1. So I have to take my vector 1, wherever its origin is, right, and I have to flip it around so it's pointing in the exact opposite direction. Same length, opposite direction, because I flipped the sign. So if that's the case, it's going up like this. I will draw it now down, same length, in the opposite direction. There's my minus 1. Okay, so what I really have now, I don't have 1, I have minus 1, and I have 2. So if I want to add those things up, well, I need to take 2 and slide it over to the head of 1, right? Sorry, the tail of 2 needs to go to the head of 1, or vice versa. So if I put 2 on 1 here, well, that's quite right, but here's my vector 2. And now notice my resultant vector is actually headed down like this. And again, if I'd drawn, my 2 and kept my 2 steady and moved my 1 over, my negative 1 vector over, you'd see I end up with things at the same spot. My negative 1 vector, it all ends up the same. But notice, 2 minus 1 is not the same as 1 minus 2. 1 minus 2 got me a vector that was pointed this way. 2 minus 1 got me a vector pointed that way. You see that? It's the exact opposite direction. It is flipped, okay? So you still have negatives and positives in here, but you have them in terms of, direction now, okay? Just like you would for addition and subtraction. So this is graphically, that's all well and good. This is probably not the thing that we're going to use most, but I do want you to see this so that you can actually see what it looks like and get a feel for it, a visual feel for what this should look like when you get done with it. So how in the heck do we actually add these things? Well, this is where it gets interesting, okay? If you want to actually accurately add these things, I'm going to leave this one in place. I'm going to get rid of this guy, okay? If you want to accurately add these things, which you actually have to do, in fact, I have these here, so let me just do that, okay? I have to take, and this is probably going to be the easiest way to do it mathematically, okay? If I want to get a nice, correct answer without having to draw things out completely exactly, what I have to do is I have to get, so let's say, do this, I have to get an x, and I have to get a y component for them. Okay? If I split these vectors up into an x and a y, those components, then I could just actually add them together. Okay? So let's say that one has a length, okay, so its magnitude is, let's actually just call it 10, okay? And for the other one, let's just call it 2. Let's make it a lot shorter now, okay? So this one has a length of 2 at that direction. Now, the other thing you're going to notice is that you need to have the angle on this. So let's say that this 10, okay, so 2 here, maybe let's add a 10-degree angle, okay? And this 10, right, the first vector is going to be at a, let's call it a 45-degree angle, okay? So now I actually have to get my x and my y components, and again, to do this, I have to use my trigonometry equations. So if I want to know this, 10 is my hypotenuse, y is going to be my opposite, okay, and x is going to be, so let me redraw this. For my first vector, 10 is my hypotenuse, my x component is going to be adjacent, right? Adjacent to that theta, or that angle, and my y component is going to be my opposite to theta, okay? So if I want to find my y component, I will have to do sine of theta is equal to opposite, or in this case, y, right, over my hypotenuse, which my hypotenuse here is 10. And my theta, we have that value, it's also 45 degrees, we said, right, or what, pi over 4, yeah. So 45 degrees or pi over 4 should get you the same thing. So if I want to find y, my y component for vector number 1, this is what I have to do, but I have to rearrange it to get y by itself, right? So that means multiplying both sides by 10 here, 10 cancels out, and it leaves me with y alone over here. So it turns out my y component over here is going to be 10 times sine of 45 degrees, right? Well, what's my x component going to look like? Well, I have to figure out my x component, okay? So for my x, that's adjacent, so I have to use cosine. So cosine of my angle, which I'm going to go ahead and just call it, I'm going to do what I did last time. Cosine theta is equal to adjacent over hypotenuse, okay? Well, my adjacent is actually the x component. That's what I really want to find. We're calling it x, okay? My hypotenuse, we have a number for that. It's 10. And my theta, we have a value for that as well. It's 45 degrees, or again, pi over 4, okay? So if I want to get x by itself to be able to find this component, I will take and move the 10 over, okay? There it goes off of that side and onto that side. So I end up with 10 cosine of 45 degrees, and there you go. Now, if you work out the same thing for vector 2, which I'm not going to take all your time to do that, you'll find out it's going to be 2 times cosine of 10 degrees, all right? And 2 times sine of 10 degrees to get my y component. When you find the values of those, how do you add them together? Very simply. 10, this one, whatever that number ends up being when you put it into a calculator, plus this one gets you your total vector for the x, right? This one plus this one gets you your y, okay? And what are those things? Those are the components of my resultant vector, r. So you'll have the x and the y of r. And if you want to find the actual value of that, you can use Pythagorean theorem, or you can use, some trigonometry, use tangent with the two pieces to actually find your hypotenuse later on if you want to, after you get your angle. Easiest way, probably Pythagorean theorem. So that's vector addition, okay? It's very simple in this case. What about this? There's a couple of different ways in which you can see vectors, okay? Another thing you can see sometimes is you can actually have, let's go ahead and say I have vector 1. Okay, this is just a different format of seeing it. Instead of giving you a magnitude and a direction, that's polar coordinates, okay, they can actually just list out basically your x, y, and sometimes your z as well. And a lot of times you're going to see these kind of like, arrow brackets on either side here. But it'll just tell you, you have 1 and you have a y of 5, right? So your vector would be 1 over 5 up, okay? That's what vector 1 would look like. Vector 2, if you want to add that one in, here's your components. It'll say 5, comma 1, okay? So it'd be 5 over and 1 up. Both would have the same total hypotenuse or length of the vector, right? But in slightly different directions. So how in the heck do I find my resultant vector for this? Well, guys, you know what? It's super, super easy. When you have it like this, all you have to do is just take and add them up, okay? So my resultant vector here is going to be 1 plus 5, 6, okay? And 5 plus 1, 6. So I'll end up with a resultant vector that's at 45 degrees. And how do I know that? The two sides are exactly the same. So if you have a tangent of 1, you're going to end up with basically 45 degrees. Okay? So, a tangent of 1 over 1 or 6 over 6 or whatever else, you're going to have a 45 degree. Okay? So that's how you add these things together. Okay? This is basically engineering notation or, it's Cartesian coordinates that you're just adding up the x and the y and the z. If one of these things was negative, right, if this was a negative 5 up here, and when I add it together, I'll have negative 5 plus 1, so I'll have a negative 4, and that's just, you just do that to change it up, okay? So no big deal. Pretty easy. Graphically, you're not going to do that a whole lot. But you do need to know which direction the vector is going to end up pointing when you're done with it, so that's why I did the graphical thing. And also, I think it sets up for why the triangles work to find the x and y components of these things, so you can actually add these things together. If you had a z, one more component here, let's put a z in, just for all cases to be done here. If I had a z, you do it the exact same way as the others. So if I had a z component of 7, and on my vector 2 I had a z component of 8, really long z component apparently, what I would end up with is a z component down here of 7 plus 8, so I'd have 15. Okay? So no big deal, pretty easy. This is probably the easiest way in the world to come up with it. I can show you the Pythagorean theorem in 3 dimensions. It's actually not anything too crazy. In fact, why don't I go ahead and do that? Rare, you're going to have to come up with this. When we're doing physics, if you can do it in 2 dimensions, you can do it in 3. Okay? So 3-dimensional Pythagorean theorem. You guys ready for this? It's crazy. You're not going to be able to believe it. In fact, I'm going to write it over here so you can see it better. 3-dimensional Pythagorean theorem. 2-dimensional is a squared plus b squared is equal to c squared, right? Well, so we have a squared plus b squared plus, let's go ahead and call it c squared. This is not our hypotenuse anymore. Is equal to the hypotenuse squared. So see that? We have 3 components instead of 2 now, and you end up with the exact same thing in 3 dimensions. That's really it, okay? Vector addition, subtraction, boom, done.